Back once again. Today is July 2nd, and this is going to be day 19 on the LeetCode grind. Yesterday I was doing some problems, but impatience makes for bad practice, and I was just going too fast, so I made a lot of silly mistakes. But I'm going to do 1 hour right now, and we have some problems set up here. Make sure to join the Discord, the Hyperbolic Coding Chamber, if you get a chance. And yeah, I'm gonna jump into it. We're gonna do add two numbers, and I got a secret tip for this by the Copy Ninja. Shout out the Copy Ninja. So we should be able to do this problem, but we're gonna do some of the cards due first, and then probably do one weighted problem, and then we'll just do new problems for the remaining time. So I'm just gonna jump into it with reverse integer. So last time I did this, I think it was with it was constant time and constant space. So given a signed 32-bit integer x, return x with the digits reversed, reversing x. So it's signed, which means it can be positive or negative. Return x with its digits reversed, reversing x causes the value to go outside the signed 32-bit integer range. Negative 2 to the 31 or 2 to the 31 minus 1, then return 0. X equals 1, 2, 3, 3, 2, 1. So we take the number, we would reverse it and return it. We take the number, right, reverse it and return it. So we have to retain the sign. And we know that when we have 1, 2, 0, if you reverse it, 0 is at the front, so it's ignorable. So you could just take x to a string, reverse the string, x to an int, retain the sign, check bounds, return number. So if we do x to a string, so we'll have x string, we'll just do x dot to string. There's probably a bit shifting version of this as well. Then we'll reverse the string, and you could do this in place. We could do this in place without taking even more space. So to do that in place, we could use, I don't know if you can swap. So we'll just do left equals zero, and we'll just say start equals 0, end equals x to string dot length minus 1, and we'll do while start is less than end, right? We want to stop when they pass each other or end up at the same point, and then we'll just swap their position. So we'll save x sub string sub start, because we're going to replace x sub string sub start with s string sub end, right? And since we replaced start, we're going to replace x string sub end with temp, and then we'll do start plus equal 1 and end minus equal 1, since they're both going to be incrementing towards the center. This should reverse the string, and then we'll take x num, right? And we'll just do, so we have to take x to an integer, right, and retain the sign. So we'll just do, if x was originally less than 0, right, when we parse the int of x string, we'll just add a negative sign right here. Otherwise, we'll do parse int x string. Then you have to check the bounds, right? So if x num, right, is less than 2 to the 31, or negative 2 to the 31, so if it's out of the bounds, or x num is greater than 2 to the 31 minus 1, right, then they want us to return 0. Otherwise, we can return x num. So we have x string, x equals x dot to string, right? Then we do start, end, the last index in end. while star is less than n, we're going to swap. So we're going to keep temp. So we're missing an equal sign here. We're going to get temp equals x string sub star, which would be 1, right? And x string sub star is going to be x string sub n, which is 3. So 1 becomes 3, and then 3 should become 1, and then we increment both, and then we'll be done there since they'd be the same on the next iteration. You only want to run while star is less than n. Then we'll check x, the actual number passed in is less than 0. It's not, so we're going to return parse int of x string, which should be 321, and then we'll check if it's out of the bounds, which it isn't, and then we'll return x num. I see index. Okay, I figured that might be true, so we'll just do x string. We'll spread x as a string. Into an array, and then if we spread it into array, we should be good, and then we can just do x string dot join with no, we won't join it with anything, we'll just join it so that they all get squished back into, basically turn it back into a string. So zoom out just a little bit. So the first case looks good, and then we'll run the second case. So this looks good. This would be about linear time with constant space. Is it constant space? Well, we're creating tertiary space for an, actually no, it wouldn't be linear. It wouldn't be constant space since this number that we create, oh, it's assigned 32-bit integer, so actually it would be. If it's assigned 32 integer, then we know that it'll take up to the largest number that 2 to the 31 can create, and however many digits that might be, like 11 or 12, we'll know we'll always have to declare an array with 11, an array with 11 indices, right, to store the string that we spread into. So that would be constant space. Since for any arbitrarily large input, we would always use up to 11 blocks of memory to hold the string as an array. And linear time, because of the same reason that it's constant space. Oh, it's not linear time either, it's constant space and constant time, because we can guarantee 11 operations at max, or 11 spaces of memory at max for any arbitrarily large assigned 32-bit integer. Quick pass here, then we'll do random weighted. So we have binary tree, Inorder Traversal. So we have Inorder Traversal, which is a root tree node or null, and we have a number, which returns an array of numbers. Given the root of a binary tree, return the in-order traversal of its nodes values. The root of a binary tree return the in-order traversal of its nodes values. So we could just do this with a recursive helper function that would do LNR DFS, right? And they want us to return the in-order traversal of the nodes values, but as an array of numbers. So we could create an array of numbers. We'll have this helper function, right, in which we could pass in the root node and nums, and then we would return nums because helper would operate on nums by reference. So this helper function would take a node, which would be a tree node or null, and we'd have num, which is an array of numbers, and we're not going to return anything. And then there's one more thing we can check. We can check if root, oh yeah, well, if root is null, then we're not really going to do anything anyway. So we just return an empty array. So we'll just make sure that when we do if node, so if the node exists, right, what do we want to do? Then we want to call helper again. Yeah, we want to call helper again for node.left, right, passing in nums. And then from here, we'd like to push, right, the current node's value, and then we'll do helper node.right, and then we pass in nums. We don't have to return anything since values are automatically being saved in this by reference property nums. So this for 1, 2, 3, we do this array right here. We declare this array, call helper with root and nums. So root would be 1 does exist. So then we push on a call to the stack node.left, which would be null, right? So now we're back up here. If node, well, null, it's null, right? So we're not going to write any code. Pop this call off the stack. We're back at 1. We're going to push 1 onto the array, right? Then we're going to do helper node.right. So we're going to push onto the stack a call of helper with 2 as the root node. So does 2 exist? It does, which means we're going to push onto the stack helper.node.left, which is going to be 3. So 3 is on the stack. The node does exist, so we're going to do helper node.left. We're going to push another call on the stack with node.left, which is going to be null. And then it's not going to do anything because the node doesn't exist. We're going to pop that off the stack. We're going to go back to 3. Then we're going to push 3 onto the array, and then push a call of helper with node.right, which is going to be null. And then that's not going to add anything to the array because the node doesn't exist. We're going to pop this 3 off the stack, this call for helper with 3, because we'll be done, right? Once we pop that, the next one on the call stack is going to be 2, right? And so we already called node.left for 2, so we're going to push 2 onto the array, and then call helper for node.right with 2. And 2.right is going to be null. And then we're going to pop that off the stack, and we're going to go back to 1, which we called helper node.right. Finish this execution, and then we're going to return right back here, and we should be good. So that looks good. Time complexity of this looks like linear time, since you have to visit every node, right, to create this array of numbers in Inorder Traversal. At the same time, the space complexity I think would also be linear time, since we're visiting every node. We'd use linear space in terms of like the recursion stack frames. So first one, using recursion. This is the classical method. It's straightforward. We can define a helper function and implement recursion. So what they're doing is they have the Inorder Traversal. They create an array list, which is what we did. Then they call it, use it by reference, and they return the array. If the root isn't null, right, then we just do L and R. So you have linear time and linear space, and then you can also do it with a stack. Oh, this is the iterative. I forgot. We have to do the follow-up. Recursive solution is trivial. Could you do it iteratively? I didn't really read the iterative solution, but I do know how to do it, since I think we just did this one yesterday. Recursive solution is trivial. Could you do it iteratively? So iteratively, you would use a stack, right? But we're just going to use an array. Actually, I'm going to check the stack API just real quick. Okay, it turns out JS doesn't have a stack implementation, so I'm just going to use a list, which I don't know if you still get constant time in, but for the sake of the problem, we'll use it like it's a stack. So the way you do this, the stack is going to pretty much pretend or pretty much simulate the recursive nature of recursive functions, or that ordering, where it's pretty much last in, first out. And so we're going to have a stack, right? We're going to have a node that we call cur. It's going to equal to root. Right? I'm going to do while cur does not equal null in the stack, or stack isn't empty. Right? We're going to do another inner loop, right? While cur does not equal null. This is going to serve to go as far left as we can, right? While pushing on elements into the stack that we should return to. So we'll do stack dot push cur, right? And then we would do cur equals cur dot left. So now we'd go as far left as we can. Facet 1, right? 1 wouldn't be null. We push 1 onto the stack, try and go left, but we can't go left. We would go left, it would be null. Next iteration, cur equals null. So what do? We would be out here. In this case, we want to do cur equals stack dot pop. Now we're back at 1, right? This would be the evaluation phase, and we do nums dot push cur dot val, and then we're going to want to create that nums array, which we return ultimately at the end. We'll return it here. We have 1. So what do we want to do now? Well, now we're in at 1. We'd want to go right and then have this whole loop begin all over again. To do that, we would do cur equals cur dot right, and then we'd go into 2, right? Cur wouldn't be null because it'd be 2, and the stack would technically be empty. So then we'd be at 2 still doesn't equal null. We push 2 onto the stack, then we go left to 3, right? 3 isn't null, right? So we push 3 onto the stack and go left. All right, we'd be here, 3 dot left, which would be null, right? Then we'd go down here, cur equals stack dot pop. So we'd be at 3 again. We push 3 onto the array, go cur equals cur dot right. Well, we go back to the top. Cur is technically null, but the stack isn't empty. Then cur would still be null, right? So we'd pop the stack again, right? And we'd be at 2. We'd push 2 onto the stack. Cur equals cur dot right. 2 dot right would be null. You go back up here. 2 would be null, right? And the stack would be empty. So neither of these would run, and so we would be done there. So that looks good. This is the stack version, and they don't really give us any more explanation. So actually, I'll check how I think my implementation is almost the exact same as theirs, right? Stack.pop, then we add the value, cur equals cur.right. So we'll pass this one, and then so that was that plus the follow-up, and then add to numbers fried us. So we'll do that one. Maybe it'd be better to sort by frequency just to make this make sense. But add to numbers is already here, so we'll just do that actually. Add to numbers is already here, so we'll just do that. So I'm gonna remove this. We have add to numbers, we have L1, right, and L2, right, and we have a list node. We're supposed to return a list node. So we have linked list input, we have to return linked list output. We're given 2 non-empty linked lists representing 2 non-negative integers. So you have 2, 4, 3, 5, 6, 4. and they're both positive. The digits are stored in reverse order, so 243 actually means 342 and 564 actually means 465. Each of their nodes contains a single digit. Add the two numbers and return the sum as a linked list. So you add these two numbers, it'd be 708, it'd be 807. You may assume the two numbers do not contain any leading zeros except the number itself. So 243 and 564 reverse is 342 plus 465 equals 807, but they want us to return the output in 708, which is return. Number of nodes in each linked list is in the range 1 to 100. Since that's the case, number of nodes in each linked list is in the range 1 to 100. It is guaranteed that the last list represents a number that does not have leading zeros. So since we can have up to 100 nodes in the linked list, we can't do the thing where we simply add the number, convert the numbers to an integer in the linked list for both of them, add them together, and then simply return or convert the sum into a linked list in reverse. Since that's the case, what we can do is do carrying addition, right? So they're given the two of the numbers in reverse, which is exactly how addition would work. In a sense, we could do 2 plus 5 equals 7, right? And then 4 plus 6 equals 10, and we carry the 1 to here, do 3 plus 1 equals 4, right, for the carry, and then plus 4 would be 8, and then we could return that. So we could do temp 1, right, temp 2, right, and then we could do elementary addition, and to add them, since they're both starting at the end, you iterate while both temps exist, we could sum the numbers. So if we sum them, we have 5 plus 2 equals 7. Which means no carry. So we would have calc sum, and we need a third array, which would be our output array. I mean our output linked list. We would do output val is the value of sum but it would be sum divided by 10. So let's just say it's 5 plus 7, we'd get 13, and then 13 divided by 10 no, it wouldn't be sum divided, it would be sum mod 10. That way 5 plus 2 mod 10 still gives us 7 mod 10 gives us 7, I think. Seven mod 10 gives us 7. Okay, 7 mod 10 would give us 7, so we could put our sum equal to sum mod 10. So that would be good. But then we want to make sure there's no carry, so we would set carry equal to the sum divided by 10. So if we do 9 plus 9, that's the highest we can sum for two numbers, and we do 18 divided by 10, that would be 1.8. So we want to parseInt that. I mean, math.floor it to make it an integer then that would be our carry, and our calculating our sum has to be the sum, calc sum of T1 plus T2 plus carry. T1 plus T2 plus carry. Output dot value is sum mod 10, and carry equals math dot floor. And then, so while they both exist, we'll add them up, right? And so they'd have the same length. But when the numbers are slightly longer than each other, if there are still numbers left, we want to copy those numbers. Do we need to continue adding? I think we want to copy the remaining numbers. So let's just say we had 2, 4, 3, 1, 5, and like they have the thing 5, 6, 4. We add all these together, that'd be 4 and 7, right? And we just have to copy 1 and 5 in the remaining longer list back into the output. But let's just say there was carry. Say this was 9, and this was 8, so it'd be 11. Our carry would be 1. We'd go to 9. We'd go to 9. And we'd still have to carry that final number, because we can only propagate one last time. So 11, put 0 here. Let me get, oh no, I don't think it propagates one last time. We get 11, our remainder would be 1. We put 0 here, we put 1 on 5. What if 5 was 9? Then it would keep propagating. Basically, we have to keep going just in case. So while temp exists, and maybe you could fuse this all together actually if you just do while either exists, either temps exist, right? And then we could just have some special code to make sure that it evaluates to 0 if it has nothing to offer. So let's try that. So actually, let's do it like this. We'll just say while either temps exist. So if we add 7 and 4, we get 11. Output dot val, right? So we'd have 7, 11. So this would be 2, and then we have a carry of 1. So while either temps exist, our calc of sum 1, which would be 9, plus T2, which would be 0, plus carry would be 1. So our output dot value would be sum mod 10, which would be 0. Carry would be sum divided by 10, which would be 1. We go to the next iteration. Sum T1 would be 5, T2 would be 0, and carry would be 1. We'd have 6. So I think this could work. You'd have const temp1 equals L1. Duplicate the line, temp2, L2, and then we have output, which is a new list node. And we got this trick from the copy ninja. I think you can just start the output linked list with new list node, and then from here, when you return the output, you can just do output. Or we actually need another one, actually, we'll just call it const temp3 equals output and then you can return output.next. Return output.next, and then we said, well, either temps exists, so while temp1 or temp2, we could calc the sum, and we'll do the sum as T1 dot val, I think. Yep, T1 dot val, and we can do it like, yeah, T1 dot val, right? And if it doesn't exist, we'll nullish coalesce to 0 plus t2 dot val. And if it doesn't exist, we'll nullish coalesce to 0 plus carry. And then we're going to need this carry variable here, which is going to start at 0. And then we'll do output dot val equals sum mod 10, and then carry equals the math dot floor of sum divided by 10. And then I think you need to do output. We do temp equals temp dot next. Temp1 equals temp1 equal temp2 equals temp2 dot next. Makes sense. We have temp3, and I guess we wouldn't even use output. We actually use temp3 dot val. Temp3 equals temp3 equals this one would be temp3 dot next equals new list node, and then we would do temp3 equals temp3 dot next. I'll have T1. I guess I should have just made these. Temp3, and then we also have these random numbers sticking out here. Temp list node sum. So our output is 0, 8, 0, which is just wrong. So let's run this. So we have 2, 4, 3, and 5, 6, 4, while temp or temp2. So const sum equals temp1 dot val, which is 2, plus temp2 dot val, which is 5, equals 7, which means temp3 dot val equals sum mod 10, which would be 7. Which would be 7. Oh, maybe I'm just supposed to return output. So it looks good. I see. So then our output is 1. We're returning 1 too many because temp3.next equals new list node. So when do we want to do that? What if we changed it so that that would still create the problem? So we could do if temp or temp2, then we could create it. Because after, we could actually would do temp dot next or temp2 dot next. Oh no, we don't need to do dot next. We already took it to dot next. Okay, that was my bad. It's right after the line for dot next, so you can just do temp. as they are. So this looks good. Temp equal temp2 dot next. Right, so when the other one is done, it's a great abuse of the nullish coalescing operator. So here we have one where our output is 0, so we're not propagating the 9s, we're not continuing the addition. So we get to 9 and temp1 still has a value in it, so we calculate the sum. So as a temp1 dot val would be 9. Well, let's just pretend it was like this, because I think it's the same problem. And 9. So we did 9 and 9, right? Temp1 and temp2, they both exist. The sum would be 9 plus 9 plus 0 would be 8. Temp3 to get the value of 18 mod 10, which would be 8. And then the carry would be 18 divided by 10, which would be 1. So we'd have 1 as a carry, and temp1 equals temp1 equals temp1 dot next. So I would go to the next 9. Temp1 equals temp2 dot next. I would go to null. So temp1 or temp2. So temp3 dot next. So we create a new list node. So temp3 dot val would get the value of 1. We create a new list node. Then temp3 would equal temp3 dot next. So we'd be at 9, and we'd be at 1, right, with the carry of 1. So then temp1 says a value in it, so it'd be 9 plus 0 plus 1 would be 10. Sum mod 10 would be 0. Would be 0. And then carry would be sum divided by 10, which would be 1. And then if temp1, so, and then, okay, so now it'd be at 9. If temp, so that would still exist. Temp3 next, so we have another node, right, which would be 0. Temp3 equals temp3 dot next. So it'd be up here. The sum would be 9 plus, so we would get 100. I'm not seeing what the problem is. Oh, I see what the problem is. If there's one carry left over, so if we do if carry is greater than 0, then we want to do one last one. We'll do temp3 equals new list node carry. Or we could add one final case actually. Let's go. Okay, so that would be the carry here. So we can compress this whole thing if we just say, hey, if the first number exists, if the first list exists, or the second list exists, or carry exists, then we're going to just do it, right? So I think all the duplication leads to a case where we actually should have just a bunch of ors. So the time complexity of this is looking like L plus L1 plus L2, because you have to visit every node. Yep, you have to visit basically every node in both. And the space would be constant space, I guess, since we're not really declaring any space that's going to scale with the output. I mean, if we ignore the output, we can't say it. I would think that we don't have to include the output in the space test. But I learned that when I have my pseudocode, once I've put one iteration into it, I should just delete the pseudocode because it just makes it hard to look at the code. So keep track of carry using a variable and simulate digits by digit sum starting from the head of the list, which contains the least significant digit. So L1 and L2, which kind of looks like 11 and 12, right? We do 2 plus 5 equals 7, 4 plus 6 equals 0, carry equals 1, right? 3 plus 4 plus carry equals 8. Just like how you would sum two numbers on a piece of paper, we begin by summing the least significant digits, which is the head of L1 and L2. Since each digit is in the range 0 through 9, summing two digits may overflow. For example, 5 plus 7 equals 12. In this case, we set the current digit to 2 and bring the carry equal to 1. Since we can set the current digits to 2, it's the remainder of the sum modulo the base. Carry must be either 0 or 1 because the largest possible sum of two digits, including the carry, is 9 plus 9 plus 1, which is 19. Pseudocode is as following: initialize covariant node to dummy head of the returning list. Initialize carry to 0. Loop through list L1, L2 until you reach both ends and carry is 0. As we see end of L1. Set X to node L1's value. If L1 has reached the end of L1, set to 0. Set Y to node L2's value. If L2 has reached the end of L2, set to 0. Sum equals X plus Y plus carry. Carry equals sum divided by 10. Create a new node with the digit value of sum mod 10 instead of the current nodes. Next, then advance the current of next events, both L1 and L2. Return dummy head's next node. So I didn't have to return dummy head's next node for some reason. Maybe that's because we're using they did the same thing. While L1 or L2 or carry does not equal 0, then they're also using their own version of nullish coalescing here. Column sum, carry equals column sum, new node equals list node of column sum mod 10, which is the remainder. Cardinal next equals new node, dummy head equals list node 1, dummy head dot next. Oh, so you don't need an extra variable. No, wait, what? No, you still do. Carry equals dummy head. New node equals list node. Cur.next equals new node. Max of mn. Assume that m and n represent the length of L1 and L2 respectively. Algorithm above iterates at most max. M. Above iterates at most max of mn times. I see what they're saying. We don't actually have to do work every time we visit both nodes. So I said m plus n. But since their work happens in the same loop, it's just the longest of the two. That makes sense. Length of the new list is at max m plus n. Interesting. That was a fun problem. So that would mean that we did add two numbers. Then we'll just do LRU cache as our next one. Give it a shot. 15 minutes left. Design a data structure that follows the constraints of an LRU cache. So we have class LRU cache, constructor, capacity, and a number. Okay. Capacity, we have a get, which takes a key, which is a number, and returns a number. We have put, which takes a key and implements a value. It looks like kind of like LRU cache, kind of looks like a map. Design a data structure that follows the constraints of the least recently used cache. Implement the LRU cache class. LRU cache in capacity, initialize the LRU cache with positive size capacity. Int get int key, return the value of the key if the key exists. Get. Initialize the LRU cache with positive size capacity. Int get int key, return the value of the key if the key exists, otherwise return -1. Okay. Put update the value of the key if the key exists, otherwise add the key value pair. Update the value of the key if the key exists, otherwise add the key value pair to the cache. If the number key exceeds the capacity from this operation, evict the least recently used key. Must each return so average time complexity. So I'm thinking we can back this up with a I think we can back this up with a reference to a map, and we could have two maps. The first map, which literally just keeps a track of the actual value for it. Oh wait, and we have to iterate over every the last recently used. Technically, you could do this. The time function get and put must return an average time complexity. Because we need a way of instantly knowing. I think we need it instantly knowing the least recently used. So maybe we could keep track of the least recently used, maybe with a stack. So maybe if we kept track of the least recently used with a stack, then we could have a map for the get and put operations, and this map would be of type number to number, and this array would just be an array of numbers. And what we would do when they want to get a key, oh, does get technically count as last recently used? Maybe get does count. Does get or put count as a least recently used, or does only put count? So evict the least recently used. With the LRU cache class, the positive capacity, maybe we could just say this dot capacity equals capacity. Then we have get key colon number colon number. So when we get a value, you just get it from the map. We want to do least recently used, something with bits. Doesn't make much sense. So if this get, we want to know if we're going to get the value, if we had some sort of auto sorting structure, maybe there could be an internal cache. There'd be one thing that would store them all, and maybe another map, which would be the cache. Well, this is the cache. The LRU cache keeps track of the most recently used value so that it's cached. Functions get and put get and put down it follows the constraints. I don't know if get or put. Oh, we can check the output. So we capacity of 2, cache is 1. Cache is 1 equals 1, 2 equals 2. So we get 1, we return 1. Get, now we put 33, the LRU key was 2, evict key equals 2, cache is equal to 1. Get return 2, negative 1. We get 2, returns negative 1 because it's not found. We put 4, LRU key was 1. Now why is it 1? Least recently used. We just put 3, so it seems like least recently used. See, that's what's strange though. If you put 1 and then 2, isn't the least recently used 1? Well, they get 1, then they put, so okay, so if you get 2, that means, so you have 1 and 3. Now if we get 2, there's nothing in there. If we put 4, well, LRU key was 1. How is it 1? Well, we got 1 once. I guess put counts for 2. LRU equals 1, evict key 1, cache 4. So it looks like get counts for 1 and put counts for 2, which means we need some way to track of it. Two to the 10 to the 5th calls we made to get and put. Called as such. That is very strange. So if 2 counts for 1, 2 counts for 1, put counts for 2. I think I'm gonna have to call it. It's 53 minutes and I have to use the bathroom very badly.